Okay, we'll be going over homework 3, part B. We'll implement a code to calculate dew pressure, bubble pressure, temperature using the NRTL activity coefficient model. Calculate and create TX, Y diagrams for the isopropyl water systems at pressure of 101,325 pascals, and we'll compare the location of the azeotrope in your plots to find to what's online. So we'll go back to this equation that we had here. It's this one. We have our activity coefficient in here, and we'll do the bubble point pretty much. So the bubble point, we know that the mole fractions of our y will add up to 1. So when we do that, this turns into a 1, and that cancels out, and we're just left with our pressure, which is our bubble point, and we'll have this left side of the equation right here to calculate it. So we'll move on to our Python, and we'll implement this. Okay, so we have our information right here. So we can go ahead and start defining a function for our bubble point. RNRTL. And it's going to be a function of Z, our composition, and our temperature. Okay. So okay, so the first thing that we need to define is our gamma, which is our activity coefficient, and we went over on the previous video. At the end, we had a function that we could use from our props to find our activity coefficient. So that would be P dot NRTL, and then we have our X and T that is inputted, and then we have our partial pressures, which is equal to our bubble point, kind of, which we already said was equal to our left side of the equation, which is our XI, PSAT, and our activity coefficient. So we can go ahead and do that. So we have our Z, or X, and then we have our times our activity coefficient times our PVAT at temperature T. Okay, so that's what will be our partials. So we basically, well, it's not our bubble point, I guess, yet. We have to add up all of our partial pressures. So we can just do P equals PI dot, or JMP dot sum PI. Okay. And then problem. Oh, that should not be a. That should be an X right here. Okay. And then we want to return our bubble point, of course, and we want to know our compositions. So we can go back to here, and we can see that our composition is right here. So we're going to just divide our PSAT over our P, and that'll give us our, or I guess it's the other way around. We'll divide our P over to our, wait, hold on, let me think real quick. Actually, yeah, it would be our PSAT over our partial pressures. So yeah, so we want our X. So yeah, that makes sense. So we have our P, and we have our PI over P in order to get our compositions. Okay. This P is no good. What's going on with our P? I want to return. Oh, that's why. Let's put that wrong. There we go. Okay, and shift enter. And then we can go ahead and hit bubble P and RTL. And we'll input our temperature in our composition, so Z and X. And it should return an array. X is not I'm at T. Says no object. Oh, I meant, okay, so we need to pull out the gamma. I didn't specify what we wanted to pull out. There we go. Okay, so looks like we have a bubble pressure of 2200, 625, and this will be our compositions correlating here. So isopropanol 0.62 and our water 0.38 around. So next thing we'll move on to is our dew point. So we'll actually be looking at the bubble temperature instead. So be looking with this equation once again. So this P sat right here, when we're looking for our temperature, we'll have a T that is dependent on the saturation. Our saturation is going to be dependent on our temperature, and our vapor mole fraction is still going to sum to 1. So this will sum to 1 right here. And then, so this will be 1, and then we'll minus our P over. So it'll end up being our liquid mole fraction times our P saturation dependent on T. Our activity coefficient minus P is going to be equal to 0. And we can use the Clausius-Clapeyron equation. And this will allow us, see if I can find a good one here. Yeah, we'll go with this one. So this equation right here, it relates P1 and P2 and T2 and T1, which helps us because we are looking for a temperature, or we're looking for second temperature and 2 pressures at that point. So we can use this and get T2 by itself. So we can go ahead and isolate that. We can take times our R over and divide our HVAP. So we'll have R times our ln P1 over P2 divided by our HVAP. We'll want to add our 1 over T1 over, and then this will all be inversed to flip our 1 over T2 over. So it'll all be inversed. So that's what we'll use, or a method that we'll use in Python. So we can go ahead and define bubble P and RTL. I spelled that wrong. Spelled it way wrong. Okay, we'll go ahead and add in our other constraints. So we have pressure equals 101, 3, 5, 2, 5, 101, 5, 2, 5, 101, 3, 2, 5, 101, 3, 2, 5. 2, 5, so that'll be our pressure, and then we have our R value, which is just going to be 8.314. Okay, and then we want to find a function here. Actually, okay, so define our T estimate here, and we want our inputs to be our P and our X. Okay, and then we'll have a set, or we want to input our Clausius-Clapeyron equation that we defined. So our inverse of our R times our NP dot log of our pressure, which is 101.325, or our normal boiling point pressure, and then divided by our other pressure that we don't know yet, and then we want to divide this by p dot p vap of our t, and then we want to add 1 over p times our we want our p dot tbn, our tbn. So that's our normal boiling point. Pick that up. Okay. Oh, and this should be H because we want our HVAP, not our PVAP. Shift enter or Alt enter, and just to make sure this works, we'll return our, or not return, we'll do our T underscore S, and we'll do our pressure, which is 101,325. 325, and we'll do our Z composition. Just make sure this runs. Oh, log. Alright, yep, so there's our return value right there. We have our temperature for each one. Okay, we can move on to, so this was a good initial guess right here, or right here, but we need something better than that, something more accurate. So we can use a optimized root scalar option. So we'll define, and this will be our actual bubble T, right? Yeah, it's okay. So our bubble T, oh yeah, we need that. We don't really need it, but it's to help stay organized. And then we want our X and P, because those are the two things that are staying constant with this. Okay, and then we want to return np dot root dot, wait, we want np dot optimize dot root underscore scalar, and we're going to define a unknown function lambda, and our T will be our bubble point. So this is right. So right here, we want to call back our bubble point because this is basically calculated that left side of the equation right here, and we're going to subtract our P, and this should equal 0 right here, and we only want that first index because that's what actually gives us the pressure right there. So we'll move on, and we'll want to do our method is our, no, we want our x0, we want our initial guess to equal our T estimate, and this will be our X and, or no, our P and X. Okay, so that's our initial estimate. Method, we want newtons, or Newton, and we just want the root because we want the 0. So shift enter. We can go ahead and I guess define it or go through it real quick and make sure it works. So we just basically take this, Control C, Control V, shift enter. X is not defined. Oh wait, we don't want this. We want this to be our Z. And then module numpy as no attribute optimize. I typed that in wrong. Okay, I think this should be SP. Maybe it's not an MP. It's shift enter. It's a different failed to converge. That means something is wrong with this right here. Let's see. So I forgot we needed a weighted boiling point. So we need to go up here. So we have np.sum, and we need to times all of these by x. And put another parentheses right here. And let's see if this works now. Yeah. Okay. There we go. So we have our 353.46 for our temperature right there, and we can move on to the next part. Okay. I also forgot we want to find our compositions here also. So delete this. So we want to not return this anymore. Okay, and then we want our G. So we can go ahead and grab this up here. Okay, and if we look back at our equation, we can see that we needed to divide kind of everything over here in order to, or everything over here to get our compositions that we want. So that'll end up being our, we want our composition, so we want to return this, and it'll be, we want to return our temperature, and we want to return our compositions times P VAP T VAP T divided by P. It's not. VAP is not defined. Yeah, I know that. Oh, I forgot the P. Got there. I need to call back to the props. So shift enter. So let's go ahead and check this. So bubble T and RTL, and we have our Z and have our P. TL, so we can, okay, that fixed it. So we can start on our dew point temperature or pressure, and we went ahead and drug these back from our previous video because these will be good initial guesses from the ideal gas. So we'll use that, and we'll use the our scalar again in order to find our best guess. So we'll go ahead and define our dew pressure for our RTL, and then we want our Y and our T this time. Okay, and then we'll define another one because we want a vector of our it's gonna be our equation, but we want a vector of our mole fraction, or our fractions, yeah, our mole fractions, and then it's gonna correlate to our pressure. So go ahead and do that. So we want X to equal everything except the last component. So be -1, and then we will want our pressure to equal the last vector. So pressure and then vec -1. I don't want to do that though. Okay, so we can then use this in order to or how do I want to do this? We want to return this. We want to return this for our array that we will then use in our root scalar, or our not our root scalar, just our scalar. So we'll do np dot, and we want this in rows. So underscore, and then we want our x times our p dot nrtl underscore gamma, our x and t. Okay, and then we want to times this by our pvap. Is that what I want? Let's go ahead and do it out, because I don't know. P dot our pvap of our t. And I forgot to go over this. So we know that looking for our dew point. So, and we know that our P saturated is going to stay constant during this because we're looking for our dew pressure. So our P saturated, our temperature is staying constant here. So this whole side will stay constant, which means we want this side to equal 0 in order for our guess. So let's just subtract this over and set that side equal to 0 in order to set up an equation that we can use. So dot there. Pvap, we want this to stay in there. So pvap t, and then minus our y times our p. Okay, and then we can also do another equation, our np dot sum of our x's, because we know those are going to add up to 1, and we can do it to -1, and that should equal 0 because all of our sums should add up to 1. So that will be another thing, and oh, we want this to be an array. Yeah. Okay. So we return that, and then we can go back to our original function and start setting up for our scalar. So we want to go to get our initial gas, which would be our old dew equation. So dew p, which I have above here. Is that what it is? Yeah. All right. Let's do p, and then we want it to be our z, or our y and t. Okay, and then we go ahead and do our root optimize, or just not a root optimize, just our SP optimize for that. What we want. Okay, yeah, I forgot to unpack our dew point right here. We want to unpack this so that we can use it in our initial guess that we want. So we'll go ahead and do that. So we'll have our p and our x equal to that, and then we'll make this our I think we want this our x and p right here. So we want this to be our x because of our guess right here, our xp, and then we don't want this yet, or at all really. So we want to pull out our x, which is going to be so we want to pull out our x right here and our p's, which is going to be, because of our vector, this is going to be everything except the last one, and this is going to be everything besides the last one. And then we'll pull out our pressure, because that's what we want to return, and our x times our p nrtl is halfway right. We want our gamma, though, of our x and t, and this is just rearranging the equation in order to get our mole fractions, and then divide by our p. Okay, and then when we do this, divide by our p. I don't want that. I don't want that. What are you doing? I don't want that. Escape. There we go. Okay. Do, and then we have our p, nrtl, yt, except our y is going to be our z. And then, wait. I don't want that there. Shift enter. And then Control V, shift enter. is not defined. Where is it at? Pbat. Yeah, okay. There we go. Actually, we just need to plot our x's right here. So we don't need to do any of that. We already calculated it. So we have our pressure and we have our compositions. So we'll move on to our dew point temperature. Okay, so our dew temperature is going to follow basically the same process, just with different variables. Since we're solving for different variables, we are going to want our P right here, because we don't know our temperature. And then we want our T right here. We want our T right here, and we want this to be our dew temperature. And then we'll have to get our, we still want that to be our Y, I think, and then change this to T. Change this to T, and then we want and change this to T, and I think that is it. Shift enter, and then we can see if this works. Do, or we want this to be T. So shift enter. Do T underscore and RTL, and we'll still have our Z, but we want our pressure now, or our pressure. Yeah. Shift enter. Can add X. It's not associated with a value. That's 7. That means I need to change something up. So that's what it was. I accidentally changed this to T, but that's what we're trying to solve for. So it couldn't execute the function right there. But now that that's changed, it executed the function, and we have our compositions, and we have our dew temperature right here at 353. So we can move on to graphing these and comparing them to what we find on the web. Okay, so I made a mistake up top here. Where was it? It was when we were defining our equation right here. If you look at it, I had the same one up here. I just had the minus y up here. It should be divided by p minus y though, in order to set the other side equal to 0. Should not be minus y. It should be over p minus y in order to set the right hand side equal to 0. So, and for the graphs, I just copy and pasted. Oh, yeah, I got that open. Yeah, sorry, I was looking back trying to fix it. I was having some major issues. But yeah, so anyway, I copy and pasted this from a earlier video we did, where basically we have our x's linearly spaced from 0 to 1, that 101. And then we have an open bracket for our t's and y's. And for x, in those x's right here that we split up, that is our counter right here. It'll calculate those in terms for our bubble t. It'll calculate those each time in this for loop. It'll append it to our t's and y's right here, and then we'll split those down into rows so that we can split them up, and just add it to our scatter here, and we plot them, and these are our results. Okay, so we have our azeotrope right here. Zoom in on it. It's about at 0.68, 0.67, 0.68, about right here, 0.67. So that's our azeotrope. It's where we have kind of a vapor-liquid equilibrium right there. and where our liquid and vapor mole fractions are equal to each other, I went ahead and where is it? Here it is. Use this one. So this is run at 60,000 kilopascals, and it is right around pretty close to about 0.69, something right there. I mean, we could jack up the pressure here if we wanted to 60,000. And just leave this right here. And then run this all again. And go ahead and enlarge it. And it's about at 0.67 still again, maybe a little bit higher. And I don't know, that, I mean, it's pretty close. That's about, I mean, it's close enough. You can't really tell exactly how close the azeotrope is on that picture right here, but it's pretty close. But yeah, so that's our azeotrope right there, and it compared pretty well to our two pictures. So that is it for this part of the assignment.